My dear students, welcome back to our channel. In this video, I will be explaining the BSc 5th semester subject Mathematics, Linear Algebra as prescribed by Osmania University and other universities of Telangana. We will go through the important questions and answers one by one. Let's begin with a quick revision. Unit 1 first important short question is: define a vector space and given an example of vector space, V.imp. Answer: a vector space is a collection of objects called vectors, where we can perform two main operations, vector addition and scalar multiplication, and the results always stay within the same set. These operations must follow certain rules like commutativity, associativity, distributive laws, existence of zero vector, and additive inverse. In simple words, a vector space is a place where you can add vectors and multiply them by numbers, scalars, and the results still belong to that space. Example: let's take our superscript 2, the set of all ordered pairs of real numbers. Our superscript 2 is equal to x, y, vertical bar x, y r. Here, addition x, y plus x, y is equal to x plus x, y plus y. Scalar multiplication k, x, y is equal to kx, ky. Both operations satisfy all vector space rules, so our superscript 2 is a vector space over real numbers. Tip to remember: think of a vector space like a mathematical playground where vectors can move, stretch, and combine freely. Next important short question is: to prove that the intersection of two subspaces is again a subspace, V.imp. Answer: let H and H be two subspaces of a vector space V. We need to prove that their intersection, written as HH, is also a subspace of V. Proof: 1. Since H and H are subspaces, both contain the zero vector 0. 0H and 0H. 0HH. 2. Let U, VHH. This means U and V are in both H and H. Because H and H are subspaces, U plus V is in both. U plus VHH. 3. For any scalar k, since U both H and H, Q will also belong to both. Q HH. Thus, HH satisfies all three subspace conditions. Example: in our superscript 3, let H is equal to x, y, z, vertical bar x is equal to y. H is equal to x, y, z, vertical bar y is equal to z. Then HH is equal to x, y, z, vertical bar x is equal to y is equal to z, which is a line through the origin, a subspace. Tip: intersection keeps only common elements, so rules still hold. Next important short question is: verify whether the set 1, 1, 2, 2, 2, 4, 1, 3, 4 is linearly independent. Answer: we want to check if the vectors V1 is equal to 1, 1, 2, V2 is equal to 2, 2, 4, V3 is equal to 1, 3, 4 are linearly independent. Step 1. Write the definition. They are independent if the only solution to C1 V1 plus C2 V2 plus C3 V3 is equal to 0, 0, 0 is C1 is equal to C2 is equal to C3 is equal to 0. Step 2. Set up the equations, component-wise. C1 plus to C2 plus C3 is equal to 0. C1 plus to C2 plus 3C3 is equal to 0. 2C1 plus 4C2 plus 4C3 is equal to 0. Step 3. Subtract first from second. C1 plus to C2 plus 3C3. C1 plus to C2 plus C3 is equal to C3 is equal to 0, C3 is equal to 0. Step 4. Use C3 is equal to 0 in first equation. C1 plus to C2 is equal to 0, C1 is equal to dash to C2. Choose C2 is equal to 1, C1 is equal to minus 2. This gives a non-zero solution, 2, 1, 0. Step 5. Quick check, shortcut. Notice V2 is equal to V1. That single observation already shows dependence. If one vector is a scalar multiple of another, the set is dependent. Conclusion: the set is linearly dependent. Memory tip: always first glance for obvious multiples, easy win. Next important short question is: if a vector space V has a basis set B is equal to B1, B2, Bn, then prove that any set in V containing more than n vectors must be linearly dependent. Proof: simple steps. Let V be a vector space with a basis B is equal to B1, Bn. Take any set S is equal to V1, Vm in V with Mn. We show S is linearly dependent. Each Vj can be written from the basis. Since B is a basis, it spans V. So for every Vj, there exist scalars a 1j, unj with. Vj is equal to a 1jb1 plus a 2jb2 plus unjaban. Form a linear combination equal to 0. Consider unknown scalars C1, Cm and the equation C1v1 plus Cmvm is equal to 0. Substitute the expressions from step 1 and group coefficients of each basis vector by. This gives a system of n linear equations in M unknowns Cj. More unknowns than equations non-trivial solution. A homogeneous linear system with more unknowns than equations always has a non-zero solution. So some Cj are not all 0 and yet the combination equals 0. Therefore, S is linearly dependent. Memory tip: think more vectors than basis slots, at least one extra must be redundant. Example: in R2, basis size 2, any 3 vectors are automatically dependent. Next important short question is: show that the mapping T, V3, R, V2, are defined as T even, a 2 a 3 is equal to 3 a 1 2 a 2 plus a 1 dash 3 a 2 dash 2 a 3 is a linear transformation. To prove T, R3 R2 given by is linear, we must show it preserves addition and scalar multiplication. Note: simplify the first component. 1. Additivity. Let U is equal to homogeneity, scalar multiplication. For scalar lambda, both properties hold, so 'tis a linear transformation. Quick memory tip: acts like a matrix multiply. If it equals Ax, it's linear, easy to remember. Next unit 1. Long questions. First important long question is: prove that the column space of an Mxn matrix A is a subspace of Rm. Idea in simple words: the column space kernel A is all linear combinations of the columns of A. To be a subspace of R, it must I contain the 0 vector, 2 be closed under addition, and 3 be closed under scalar multiplication. We check these 3 things. Setup. 1. 0 vector is in kernel A. Take all scalars x underscore j is equal to 0. Then 0 c underscore 1 plus 0 c underscore n is equal to 0, the 0 vector in Rm. So 0 kernel A. 2 closed under addition. 3 closed under scalar multiplication. Take U is equal to underscore. Again a linear combination of the columns. So alpha kernel A. Therefore kernel A satisfies all subspace conditions, so it is a subspace of Rn. Quick example, to remember columns are like ingredients. Any dish, vector, made by mixing ingredients, columns, stays in the kitchen column space. Adding to dishes or scaling a recipe still uses the same ingredients, so you never leave the kitchen. Next important long question is: find bases of the null space and the column space of the matrix. A is equal to. Given matrix A is equal to. We need basis for the column space, kernel A, and the null space, null A. I'll show clear steps and the final basis. 1. Reduce mentally find pivot columns, idea. Row reduction, or checking linear relations among columns, shows the matrix has rank 3. That means 3 columns are linearly independent and span the column space. The pivot columns are columns 1, 2, and 4. So those 3 columns form a basis for kernel A. Column vectors. Basis for column space, choose pivot columns 1, 2, 4. These 3 vectors are linearly independent and every column of as a combination of them. Quick check relation. So C_3 is redundant. 2. Null space, solve Ax is equal to 0. Solve the homogeneous system. One free variable appears, the null space is one-dimensional. A convenient non-zero solution is x is equal to. Because A, 9, 5, 1, 0, t is equal to 0. Thus null space is all scalar multiples of this vector. Basis for null space. 3 dimensions, rank, nullity check. Rank A is equal to 3 dimension of kernel A is 3. Then null A is equal to 1. And 3 plus 1 is equal to 4, number of columns, as rank nullity theorem predicts. Answer summary, easy to remember. Basis of kernel A, 2, 2, 3, t, 4, 5, 7, t, 1, 3, 6, t. Basis of null A, 9, 5, 1, 0, t. Memory tip, pivot columns column space basis, free variables null space basis. Next important long question is: find basis of the null space and the column space of the matrix. A is equal to. Answer, simple steps, easy to remember. Given the matrix, 3 times 5. A is equal to. We will find a basis for the column space and for the null space. 1. Column space, kernel A. Idea, column space is equal to span of column vectors of A. The pivot, independent, columns form a basis. Row reducing or looking at RREF shows pivots in column 1 and column 2. So columns 1 and 2 are independent and span all columns. Take those columns from A. Basis for kernel A. Memory tip, pivot columns column space basis. 2. Null space, null A. Idea, solve Ax is equal to 0. Use RREF to get equations for x_1, x_2 in terms of free variables. RREF gives the system. Let free variables. Then. So the general solution is x is equal to. Thus null A is 3-dimensional and a convenient basis is the 3 vectors above. Basis for null A. Memory tip, number of free variables is equal to number of null space basis vectors is equal to 5 rank is equal to 3 here. Quick summary. Basis, kernel A is equal to. Basis, null A is equal to. Next important long question is: show that the set of all real polynomials over the field of real numbers is a vector space with respect usual addition and scalar multiplication of polynomials. Answer. Let P, R be the set of all real polynomials. We want to show that P, R is a vector space over with usual polynomial addition and scalar multiplication. 1. Closure under addition is also a polynomial. Sum of two polynomials is still a polynomial. 2. Closure under scalar multiplication is also a polynomial. 3. Zero vector. The zero polynomial 0, x is equal to 0 is in P, R. 4. Additive inverse. For P, x, P, R, P, x is also a polynomial and 5. Other vector space properties. All other axioms, associativity, commutativity, distributive laws, scalar multiplication laws, are naturally satisfied by real numbers. Conclusion. Hence, the set of all real polynomials P, R is a vector space over R. Memory tip: think of polynomials like flexible vectors of any degree. You can add, stretch, or scale them freely and still stay in the polynomial world. Next important long question is: if a vector space V has a basis of n vectors, then prove that every basis of V must contain exactly n vectors. Answer. Let V be a vector space with a basis B is equal to B underscore 1, B underscore 2, B underscore n. We want to show any basis of V also has exactly n vectors. Step 1. Suppose another basis exists. Let B is equal to V underscore 1, V underscore 2, V underscore m be any other basis of V. By definition, B is linearly independent and spans V. Step 2. Compare sizes using linear dependence. BSPANS V, so each V underscore JB can be written as a combination of vectors in B. Key idea: a set of more than vectors in V must be linearly dependent, since Bhasan vectors. So if Mn, B would be linearly dependent. Contradiction. Similarly, if Mn, it cannot span V. Contradiction again. Step 3. Conclude. Hence, M is equal to n. Any basis of V must have exactly n vectors. Memory tip: think of the basis as slots for independent directions. There are exactly n slots, no more, no less. Extra vectors dependent, fewer vectors cannot span.